All right, let's dive right into this explainer because today we're tackling one of the most common and, honestly, most painfully expensive failures in production machine learning. Industry estimates show a massive chunk of models just never make it to production. And when they do fail, it's often because of exactly what we're about to discuss. You spend weeks building a model, the metrics look fantastic, you deploy it, and then absolute disaster strikes. So today we are going to fix that problem for good by exploring how to eliminate training-serving skew using Feast feature stores.
Picture this. You've built a customer churn model. You trained it on a really key feature, like, I don't know, average spend over the last 30 days. During your evaluation phase, this model is an absolute rock star. 91% accuracy. You are literally ready to pop the champagne. But the very second it hits production, its performance catastrophically plummets to 74%. So, what exactly happened? I mean, your model isn't broken. The underlying math didn't just magically fail overnight.
What you're experiencing is a devastating little thing called training-serving skew. This sneaks up on you when your training pipeline and your live serving system compute the exact same feature, but they do it differently. Like maybe your production system handles null values in a weird way, or it uses a slightly shifted time window. The end result? Your model was trained on one version of reality, but it's being served on a completely different one.
Today, we're taking this silent killer down. Here's our game plan. 1. The silent killer. 2. Feature store architecture. 3. Building features with Feast. 4. Point-in-time correct joins. 5. Serving and materialization. And wrapping up with 6. Ecosystem and best practices.
Section 1. The silent killer.
Look at how things usually run without a feature store. Your feature computation logic is totally fragmented across two completely different environments. On one side, you've got your training pipeline running in batch mode, maybe using Spark, dbt, or Pandas on a huge data warehouse. But then over in production, your serving system is real-time application code hooked up to a totally different database and probably written by an entirely different software engineer. When you have two separate implementations of the exact same logic, well, you're practically begging for discrepancies.
Moving on to Section 2, Feature Store Architecture.
Now here is the fundamental brilliance of a feature store. You define your feature logic exactly once, just once. The architecture then handles serving it from two different storage layers behind the scenes. You've got the offline store, think data warehouse or data lake, holding the complete, massive historical record of every feature value. That's your training goldmine. Meanwhile, the online store, something like Redis or DynamoDB, holds only the absolute latest value for each entity. That gives you that sweet millisecond latency for live inference. It's one definition, two consumers, and zero skew.
Section 3. Building features with Feast. So how do we actually build this out? We use Feast. And Feast relies on three core concepts to keep everything perfectly identical across your environments. First up is the entity. This is essentially just your primary key, like a customer ID. Second is the data source, which literally just points to where your raw data lives, like a Parquet file. And third, the big one, the feature view. This groups your features, defines the data types, and, this is absolutely crucial, it sets a time-to-live safeguard, or TTL. That TTL is a massive production safety net. It strictly limits the maximum age of a feature before it's considered stale, so your model never ever makes decisions based on ancient history.
Section 4. Point-in-time correct joins.
Okay, I love this part. Think of point-in-time correct joins as, well, basically time travel for your data. When you train a model, your training rows absolutely must show feature values exactly as they existed at the very moment the label was generated. If a customer churned on March 15th, your training data has to show their usage and spend exactly as it was on March 15th, not today's data. If you just queried your database right now, you'd pull in all this post-churn activity, and that is a massive data leak. Point-in-time joins guarantee that your models only ever train on actual historical reality. It completely blocks the future from contaminating your past.
And the payoff here is huge. Once Feast hands us these perfectly clean, historically accurate features, we seamlessly move into training our model. Pair this with MLflow for tracking, and we get the holy grail, full lineage. By logging the specific Feast feature view and its exact version right into MLflow, every single model in your registry traces back to the exact feature definitions it trained on. Your data, your features, your parameters, and your final model. The whole shebang is beautifully connected. Section 5. Serving and materialization.
All right, so how does this get to a live production environment? We use a process called materialization. This is the bridge. It's usually something like a scheduled Kubernetes cron job that just grabs the freshest feature values from the offline store and copies them into that ultra-fast online store. But hey, quick warning here. If this job fails, and it fails silently, your online store starts serving stale features immediately. You absolutely have to have aggressive alerting set up for this. Otherwise, your model's going to be making critical decisions based on totally outdated info.
When it all comes together in our final fast VAP service, it is a thing of beauty. A request comes in, right? Just a customer ID. Our service hits the Feast online store, grabs all the fresh features in under 5 milliseconds, passes them to our MLflow model, gets the prediction, and boom, returns the response. And the absolute magic here, we are using the exact same feature definition list for live inference that we use during training. Mind-blowing, right?
Section 6. Ecosystem and best practices.
Now, if you're looking at your own stack and evaluating your options, you've really got 3 major players. Feast is fantastic. It's open source, it's Python native, and it gives you total control over your infrastructure. But if you want a fully managed enterprise solution and you just don't want to deal with the underlying plumbing, Tecton is an absolute powerhouse. Or if you're operating in a hybrid or on-prem environment, Hopsworks is a really solid platform that actually bundles a feature store right alongside a model registry.
To really succeed in production, though, you need some strict discipline. Pro tips here. First, treat your feature store like a shared organizational library. If a feature is used by more than one model, put it in the store. Stop duplicating engineering work. Second, never ever modify existing feature views. Always explicitly create a new version. And lastly, like we mentioned earlier, ruthlessly monitor your feature freshness, using those time-to-live alerts, and keep a super close eye on those materialization cron jobs.
All right, I want to leave you with a critical architectural question to chew on. We've talked a lot about customer churn today, but let's raise the stakes. How would you apply everything we just covered, the point-in-time joins, the materialization schedules, those TTL safeguards, to a high-stakes, real-time fraud detection environment? An environment where literally every millisecond matters, and a stale feature means immediate, real financial loss. Just think about how a unified feature store fundamentally changes the reliability of a system like that. Thanks for hanging out with me for this explainer, and keep building those robust ML systems.